Okay, so when we see a truss problem like this, there's two things that need to happen. And the first thing is that we need to solve for the external reaction forces, and then we can solve for the internal member forces. When I say solve for the external reaction forces, what I mean is you need to solve for the reactions or the forces acting at the support locations. So typically we're going to see one pin and one roller. And at our pin, we're going to have two reaction forces. A pin's going to prevent reactions in the X direction and the Y direction, whereas the roller is only going to prevent motion in the Y direction, and that Y direction is going to be perpendicular to the ground here. So think about those Y directions as that normal force of the truss pushing down on the ground where it makes contact with the ground. So at point C, that's going to be up. I'm going to call it RCY, reaction at point C in the Y direction. At point A, I'm going to also show it as up. Typically it's going to be up, and I'm going to call it RAY, the reaction force in the Y direction at point A. When I look at the X direction, I'm going to draw it to the left. That's because our only other force acting in the X direction is acting to the right. So for equal and opposite, it's going to have to act to the left. So I'm going to call that reaction force A in the X direction, RAX. Guys, I'm trying to record something right now, so if you can't talk, that'd be great. Okay, so we're going to start with our three equilibrium equations. We have sum of forces in the X direction equals 0, sum of forces in the Y direction equals 0, and sum of moments has to equal 0. And so these three equilibrium equations are only for part A. Sum of moments is not going to come into play in part B when we're solving for the individual reaction forces in each member. So I'm going to start by setting up my equation for sum of forces in the X direction. So sum of forces in the X direction always has to equal 0. And make sure you're always notating which direction you're acting in so you can keep track of your forces. So in the X direction, I have my 175 pounds acting in the positive X direction. And I'm going to put my RAX in the negative direction. Now because I already showed it to the left, this answer is going to come out positive. So RAX is going to come out to 175 pounds. Because I assumed that it was to the left based on the direction of this, I don't want to change this around. I don't want to change the arrow because I know equal and opposite. So I'm going to say RAX is going to be negative 175 pounds or 175 pounds to the left. Then I'm going to set up my sum of forces in the Y direction equation. And that's going to include our RAY, our 350 pounds, and our RCY. So I'm going to show RAY as positive, 350 pounds as negative, and RCY is positive. RCY and our AY are pointing up, so those are going to be positive. If I want to simplify this, I can say that RAY plus RCY equal 350. We know that, but we don't necessarily know what the distribution between those two forces is. So that's where our moment equation comes in. Our moment equation, we want to be able to solve for one of these things so that we can solve for the other one by using our forces in the Y direction equation. So it's sort of like a system of equation where we're able to eliminate one so that we can solve for the other. So we want to pick either point A or point C because that's going to eliminate one of our forces. I'm going to pick point A because there's more happening there. It really doesn't matter which one you pick as long as you're consistent. So I'm going to do sum of the moment about point A, and again I want to be clear about that notation. We're going about point A. And so remember, our moment equation is force times distance, and that's perpendicular distance. So the three things that are going to cause rotation about point A, if I held down on point A, the three things that are going to cause rotation about point A are this 350 pounds down at point B, RCY pointing up at point C, and the 175 pounds to the right at point D. And again, this is where our clockwise and counterclockwise comes into play. Remember that clockwise is negative, counterclockwise is positive. So if I start with my 350 pounds, it's going to cause rotation in this direction, clockwise direction, which makes it negative. So we're going to say negative 350 pounds times our perpendicular distance of 4 feet plus RCY. It's going to be pushing up or in the counterclockwise direction, which makes it positive, times our distance, our perpendicular distance, so 4 plus 6, 10 feet. Finally, we're going to have our 175 pounds. If we're holding down on point A, it's going to cause rotation in the clockwise direction. And so again, it's going to be negative. So we're going to have negative 175. And again, we want perpendicular distance. So our perpendicular distance is this 4 feet here. We don't want to use this hypotenuse. We want to use the perpendicular distance. So if we solve this or simplify it, we're going to have 10 times RCY equals is going to be 350 times 4 plus 175 times 4. So RCY is going to be 210 pounds. So if we then take our 210 pounds and put it back into our equation here, we'll have RAY plus 210 equals 350, which means that RAY has to equal 140 pounds. So now we have all of the external reaction forces. And I'm going to make sure that I notate pounds at each of these, just as good practice. Okay, so we have all of our external reaction forces. So I'm going to put those on my figure. Oh, I already messed up. 210 here. 140 here. And 175 here. All right. So now is when we can move on to our internal member force reactions. So I'm going to start by drawing a free body diagram of point A. I'm going to start at point A because we have two known values. We have a known value in the x direction and in the y direction, and we have an unknown AD and an unknown AB. And so we want to find not necessarily the x and y component of each of those, but we want to find truly what is the force happening within member AD. And if you link that to your truss design project, the purpose being to determine the sizing and the material that you need in order to accommodate the forces occurring within each of those members. So I'm going to draw point A. And again, I'm going to make sure I notate it. And I'm going to draw vector AB, and I'm going to call it force AB. So I want you to make sure that you're being consistent about drawing these as vectors. We're going to draw them as forces with a magnitude and direction. So the magnitude is going to be that FAB, and the direction I'm showing is the positive right direction. We are initially always going to assume that it's pointing away from our point. And by doing that, we are assuming that it is in tension. When we assume that it's in tension, if our answer comes out positive, then we know that we assumed correctly. If it comes out negative, then we know that it's in tension. So I'm going to also draw in these external forces because those are also happening at point A. We want to ignore point B and point D at this point. We are only focusing on point A. So this 175 pounds and the 350 pounds do not come into play when we're looking at point A. So we have our 140 and we have our 175 pointing to the left. So the first thing we want to do is let's set up our equation for sum of forces in the y direction. And again, here we're only using the sum of forces in the y and x direction. We're not using that moment equation. So what are the things happening in the y direction? We're going to have the 140 pounds acting up, and then we're going to have this y component of FAD. So I'm going to call that FADY. And that's also going to be shown as up. So plus FADY. So those are the only things that we have acting in the y direction. So all we need to figure out is what FAD is. So if we simplify this, we can say that FADY has to equal negative 140 pounds, right? But we don't really care what FADY is, we want to know what FAD is. So how do we figure out the relationship between FAD and FADY? That's where our trigonometric functions come into play. And so this is like determining those component parts of your vector like we did initially on our free body diagrams. And so we want to find what that y component is. And so the y, keep in mind, we can draw it here, we can draw it here, but we need to be conscientious about the angle. Because this is a 45-degree angle, it doesn't matter which one we go with. But I'm going to say that FADY is equal to the magnitude of FAD times the sine of 45 degrees. Same sine of 45 degrees because that would be the opposite side from this 45-degree angle. If I did the angle here, if I was considering this angle here, which is also 45 degrees, that would then be cosine. But just be conscientious about which angle you're using. It doesn't matter which one you use as long as you pay attention to the angle and the opposite or adjacent side that you're looking at. Okay, so if FADY equals FAD times sine of 45, we could set these two things equal to each other. So we can say that negative 140 equals FAD times the sine of 45. Or FAD equals negative 140 divided by the sine of 45. So at that point, it's just a simple mathematical solution. So we're going to do 140 divided by the sine of 45, and we're going to get about 198. And let's hold on to that negative sign, so negative 198. And so because we got a negative sign, that means that we assumed incorrectly. It's not actually in tension, it's in compression. So FAD is negative 198 pounds of compression. So we can move our arrow around. We're going to turn it around in this direction and get rid of that one. And so then that means that our y direction is down and our x direction is now to the left. So we have FADX. So if we set up an equation for sum of forces in the x direction, we're going to have negative 175. And remember, the arrow dictates the sign that we're going to use. Which direction the arrow is pointing, because it's pointing to the left, that's why we're going to use the negative. We're going to call FAB positive, because right now we have it in the positive direction. And we're going to do minus FADX. Because we know what FAD is, we can write an expression for FADX using our FAD that we found in this part. So again, we're going to say FADX equals FAD. And this time we're going to use cosine because it would be the same thing as that adjacent side if we were to draw FADX down here. We typically draw it up here so that it doesn't conflict with our forces that are part of the truss problem. So I'm going to say cosine of 45. We know that the magnitude of FAD is 198. I'm not going to use the negative there because I'm accounting for the negative by the direction of the arrow here. So we're going to say 198 times the cosine of 45, and FADX equals 140. So notice that our y and our x were the same because of that 45-degree angle. Okay, so if I rewrite my equation, I'm going to have negative 175 plus FAB minus 140, or FAB equals 315 pounds. So we found FAB, we found FAD, and we should note that FAB is in tension because we got a positive number. Our initial assumption that it was in tension was correct, and we can continue with our problem. So I'm going to move on to point B now, because we know FAB, we don't know BC, we don't know BD, but we have a known value in the y direction, this 350 pounds. So this is a simple adding up of x's and y's. We don't have to break down any of our forces into x and y components because they're already directly in the x and y. So I'm going to draw a free body diagram of point B. Point B. And we're going to have our FAD. And because we know it's in tension, we're going to draw it away from our point B. And again, we're going to let the direction of the arrow dictate our sign, but the magnitude of FAB is that 315. In this direction, we're going to have our FBC. We have our 350 pounds down, and we have our force BD up. So if we do our sum of forces in the x direction, has to equal 0. We're going to have negative 315 pounds because it's pointing to the left. Again, let the arrow dictate the sign that you use. So 315 plus FBC because it's pointing to the right. And then we can rearrange this so that FBC equals 315 pounds. And again, it's in tension because we got that positive number. We assumed it was in tension, so we confirmed that assumption by getting that positive number. If we do our sum of forces in the y direction, we're going to have our negative 350 pounds pulling down. We're going to have our positive FBD pointing up. And if we rearrange that, we're going to get that FBD equals 350 pounds. And again, that's going to be in tension because we got a positive value. So at this point, we found FAD, FAB, FBC, and FBD. So all that we need to find now is FCD. So I'm going to draw a free body diagram of point C. And at point C, remember that we have our reaction force of 210 pounds pointing up. We have our force BC, and it's in tension, so we're going to draw the arrow away from our point. And then we're going to have our FCD at that 33.69 degree angle. Again, we're going to show it pointing away. So we have force CD. It's at a 33.69 degree angle. The magnitude of FBC is 315 pounds, which we found in the previous part. And all we need to find is FCD. And so we have a known in the x direction, we have a known in the y direction, and all we need to find is FCD. So we can either use the component force in the y direction, that FCDY, or in the x direction, that FCDX. We don't need both of them because we don't really care what FCDX and FCDY are. We're just using them as a tool to find that magnitude of FCD. So I'm going to set up a sum of forces in the y direction equation. And when I initially set it up, I'm going to have 210 pounds in the positive direction because it's pointing up, plus FCDY. If I rearrange this, we know that FCDY has to equal negative 210 pounds. So let's write an expression for FCDY. Again, this is where we're using our sine and cosine, but we need to be careful about which one we're using. So FCDY equals that magnitude of FCD, which is what we're trying to find, times the sine of 33.69. So if we plug that into our equation here, we have negative 210 pounds equals FCD times the sine of 33.69. So FCD equals 210, negative 210 divided by that sine of 33.69. So let's do the math on that. 33.69 sine, and we'll get about negative 379. So FCD equals 379 pounds, and it's going to be in tension because we got that, or compression because we got that negative number. So if we were going to continue on with our problem, if there were more things that we needed to find, again, we would want to move our arrow around, and because we found compression, and let that arrow dictate the sign as we went forward. But at this point, we have all the things that we need, and we've completely solved the problem.